Hello, welcome back everyone. Today we're going to be doing Leetcode problem number 230, k smallest element in a BST. Given a binary search tree, write a function k smallest to find the k smallest element in it. So if we were given example number 1, the first smallest element is just 1. And for example number 2, the third smallest element is 3. So the problem is pretty straightforward, but you have to basically remember a trick in order to come up with the solution. So let's go over that trick. I've reproduced an example here, and using this example, we're going to go over what kind of logic is involved in coming up with the solution I'm about to tell you. So it turns out that you need to remember in-order traversals, and they're important because if you do an in-order traversal on a binary search tree, you can actually output a sorted sequence of the numbers in that tree. If you have a sorted sequence, then all you have to do to find the k smallest is access the k-1th index, and that's your answer. So let's actually do an example. An in-order traversal is defined as the following. At every node, and I mean every node, you go to the left, process the left subtree. Once you're done with that, you process the root, then you process the right subtree. So let's try to apply this to this tree. We start at the root node, which is 5, and then we process the left subtree. So that's this entire thing, which makes us end up at 3. And then we go to the left again, and then we go to the left again, but there's nothing to the left. So we go back up to 2, and we process 2. In this case, that means simply printing it out, or appending it to an array. We finished processing the root, so we go to the right. Nothing to the right, so we go back here. Then we finished the tree rooted at 2, so we go back to 3, and we process 3. So let's say we print that out. And then we go to the right, and then we go to the left. Nothing to the left, go back to 4. We have to print 4 out. Then we go to the right, but there's nothing to the right, so we go back to 4, and then we're done at 4. Then we go back to 3, and we're done with 3, so now we go back to 5. So at this point, we've covered this entire left subtree. Now we have to process 5. So that's just printing it out, and then going to the right. Here we have to go to the left, but there's nothing there, so we come back here and print 6, and then we go to the right, go to the left, come back here, print 7, go to the right, come back here, go back there, and then come back here. So at this point, we've done everything to the left of 5, 5 itself, everything to the right of 5. That means we finished processing this entire tree. So, what's our answer? Let's say we're trying to find the answer for k equals 3, the third smallest element. We have a sorted array here. All we have to do is access k-1. 0, 1, 2. This is our answer. And that's correct. This is the third smallest element. So this is very simple if you know your traversals. But there's a way we can make this faster. Notice that we had to search through the entire tree, construct the array, and then find the answer from that array. What if, once we touch the k smallest element, we return early, instead of having to search through the entire tree? Well, we could do that very easily, and let me show you how. So, using that in-order traversal technique, we can do something similar. So, start at 5, go to the left, go to the left, go to the left. Now, there's nothing to the left of 2. What does that tell us? That tells us that 2 is the first smallest element. Right? So, in order tells us to go to the left, but left has nothing, so now we're going to process the root. processing the root means asking ourselves this question. What place does this number have in my list of kth smallest elements? Okay, now we've processed the root. In order tells us to go to the right. There's nothing to the right. So we come back here, and we're finished with 2. So now we go back to 3. Now we need to process 3. It actually turns out that 3 is our second smallest element. Right, so we finish processing 3, then we go to the right, and we go to the left. There's nothing to the left, so we go back to 4. Now it turns out that 4 is our third smallest element. So what are we doing here? We're basically keeping track of the number of kth smallest elements that we've filled up so far in our traversal, and at the precise moment we've touched upon the kth smallest element, we just return that as the answer. And that's correct, because we have 4 here. So let's actually go over the implementation. First, we're going to go over the first solution, which is the recursive in-order traversal. No stopping early. So first, we're going to have a stack. Oops, not a stack. We're going to have an array to keep track of the sorted sequence of numbers we're going to get from our traversal. And then we're going to define the traversal function, which just takes in the root. Now we have our base case. If we're at a none, then we have to return. There's nothing we can do about it. Otherwise, we're going to follow the formula. Go to the left, process the root, and then go to the right. Now, we actually want the root.val here. So we're going to call this function on our root, and we're going to return the element at the k-1 of index. Let's see if that works. Okay, great. So time complexity and space complexity. Time complexity. We're going to go over the entire tree using this traversal. And the tree has n nodes, therefore big O of n. Space complexity, big O of n. Because think about what we're doing. The in-order traversal is allocating stack frames for each level you go down the tree. That means the space complexity is going to be proportional to the height of the tree. So our space complexity is linear. Now let's see. We're going to go over the second solution now. So this is actually covered in the official solutions, but let me just explain the logic behind it. We have an infinite loop, and within that we have another loop. And here we're just going to do an iterative version of the in-order traversal. So that means we're going to be using a stack to keep track of where we are. And then we're going to follow in-order's formula, which basically means we're going to move to the left. Root equals root.left. Now, while this while loop is running, that means we still have space to move to the left. Once it's terminated, we don't have any more space to move to the left, and root is none. So that means we're going to have to use our stack and basically roll back a step. Now, we also discussed that every time we finished processing the left subtree, and now we have to process the root, we're going to keep track of where this number stands in our kth smallest elements. So that's actually done in this algorithm by decrementing k. Because every time we encounter the next smallest element, we are getting closer to finding the kth smallest element. And once k equals 0, that means we just return the root.val. Okay, so let me tell you something. This is exploring the left subtree. This is processing the root. Now, in where it tells us to do the right subtree. That's simply root equals root dot right. And that's the algorithm. Let's see if it works. Okay, so notice this is a little bit faster because we have the potential of stopping early. Now notice that the time complexity here is actually still big O of n. And you might have other people adding some more variables here or naming their variables differently, but ultimately n plus anything that's smaller than n is still big O of n. And if you think about it logically, that makes sense, because even though our algorithm is capable of stopping early, it's not guaranteed to stop early. And in the worst case, we still might have to search through this entire tree, which has n nodes in it. So time is linear. Space is also linear. Because what are we doing? We're doing the same thing as last time, but instead of using an implicit recursion stack, we're using an explicit stack now. And the stack is going to be using memory proportional to the height of the tree, which could be n in the worst case. And that's it. If you like this video, please like, comment, and subscribe, and I'll see you next time. Thank you.